Welcome to this presentation on method of differentiation. Here we're going to look at successive differentiation that involves finding higher derivatives such as d2y by dx squared or d3y by dx cubed, etc. And the presentation assumes you have an understanding of standard derivatives. Looking at successive differentiation here. We're going to be given a function, something like y equals some function of x, and we're going to differentiate this with respect to x. To get our first differential equation. We'll be using two types of notation throughout the presentation. dy by dx is Leibniz notation for a first order differential equation, and f-x is Newton's notation, functional notation for a first order differential equation. So we'll be using both of these notations throughout the presentation. When we find a second differential by differentiating again, we get what is termed a d2y by dx squared in terms of Leibniz notation, or f"x in terms of Newton's notation. We can continue this differentiation process and differentiate again, get what's called higher order derivatives, such as a d3y by dx cubed, or that can be written in Newton's notation as f"x, and also a d4y by dx to the 4 f to the 4 x in Newton's notation. So we'll be looking at these higher order derivatives as we go through the examples. I'm just repeating here a table of standard derivatives. Just for reference, we'll be using these in the examples that are to follow. Example 4 here is given to us. We're asked to find the fourth derivative of the expression y equals 3x to the 4. So I'm going to use Leibniz notation here. So given y equals 3x to the 4, my first differential, dy by dx, is equal to, and I'm following the standard derivative form of ax to the n, gives me nax to the n minus 1 format. So if you follow the differential of 3x to the 4, following the pattern through, it's 3 times 4 and take 1 off the index, that's 12x to the 3. To find my second differential, my d2y by dx squared term, again following the pattern through, it will be 12 times 3 is 36, take 1 off the index, x to the 2, so 36x to the 2, the second differential. Now I go on to my third differential. Notice it's now d3y by dx cubed, and again following the standard pattern through, that would be 72x, and to get the fourth differential, the question requires d4y by dx4 is equal to a constant of 72. Exercise 4 has 4 sub-questions here. I'm going to outline 3 of these in the slides that follow. I will leave you to look at the fourth on your own, although I will provide the solution on the slides for your reference. Exercise 4, Part A. Given the function y equals 2x to the 5 at minus 4x cubed plus 3x minus 5, we're asked to find the second derivative of the d2y by dx squared. Notice the function of y, on the right hand side all the terms are all of the form ax to the n, all polynomials, so we've got our derivative form given in our table. So differentiating 2x to the 5, we get 10x to the 4, differentiating minus 4x cubed, we get minus 12x squared, plus 3x becomes plus 3, and the minus 5 constant disappears when we differentiate. So we've got our first derivative dy by dx. If I differentiate the first derivative again, I get 10x to the 4 becomes 40x cubed, minus 12x squared becomes minus 24x, and the constant plus 3 disappears. I've now got my expression for d2y by dx squared. All I've done on the final line is factorised on 4x. Just to continue the exercise 4a, this is not required in the question, but just to show you what happens if I continue to differentiate the function. If I start with the d2y by dx squared equals to 40x cubed minus 24x, and just for interest here, if I differentiate again, I will get d3y by dx cubed, and the 40x cubed becomes the 120x squared, the minus 24x becomes minus 24. If I differentiate again, the 120x squared becomes 240x, so I've got my fourth derivative. If I differentiate the 240x, I get 240, so I've got my fifth derivative, and if I differentiate the 240, I get 0. So my sixth derivative in this particular case would be 0, but that's just for reference. Exercise 4 part B, function of x is given as cos of x minus sine of x. We're asked to determine the value of x in the range of 0 to pi upon 2, that's radians of course, that's 90 degrees for the value of x, and when the second differential, the f double dash x, is equal to 0. So given the function of x, here is equal to cos x minus sine x, and again those are standard derivatives in our table. I'm showing them here for convenience. We've got sine ax differentiates to a cos ax, and cos ax differentiates to minus a sine ax. So those are our standard forms there. So when I find the first differential, the f dash x, using Newton's notation, cos x differentiates to minus sine x from the table, and the minus sine x differentiates to the minus cos x there. Okay, the a in this case, by the way, of course, is 1. When I find my second differential, my f double dash x, the minus sine x from the table will differentiate to minus cos x, and if we just consider the cos x in the bracket above, when I differentiate cos x, that will differentiate to minus sine x, but of course I have a negative outside from the original equation. So in the last line I've just simply simplified the second differential as minus cos x plus sine x, the double negatives making the positive. Exercise 4b continued, and now we're going to determine the value of x in the range 0 to pi upon 2 when the second derivative is equal to 0. So just repeating the second derivative from the previous slide. On the right hand side it's minus cos x plus sine x, and we're told the condition we have to satisfy is when the function double dash x equals to 0, so left hand side equals to 0. All I'm doing on the next line is add in the cos x to both sides to make it positive on the left hand side, leaving with my sine x on the right hand side, and I'm dividing then throughout by cos x. Just think this through. Dividing the left hand side by cos x, that's cos x divided by cos x is 1, and dividing the right hand side by cos x, that's sine x divided by cos x. Alright, so dividing both sides by cos x there. Now from our definitions of trig identities, we know that sine x divided by cos x can actually be written as tan x. So I actually get an expression that tan x is equal to 1. To find the value of x, I need to take the inverse tans of both sides. So to get x, I need to take the inverse tan, or the arc tan, of 1, and you'll find that that gives you 45 degrees between the 0 and 90 condition we're given, a 0 in pi upon 2 condition. That gives us 45 degrees, or in radians is 0.7854 radians, or pi upon 4 radians, whichever you prefer to specify. Exercise 4 part C, we're given a function of x, or if you like y equals to 2x times e to the minus 3x. We're asked to show that the second derivative of x plus 6 times the first derivative of x plus 9 times the function of x is equal to 0. So given the expression, I'm going to use the notation y here instead of function of x, just for convenience on this slide. Y is equal to 2x e to the minus 3x. That's where we start from. But we need to recognise that that is a product. We've got a function of x times a function of x. We've got 2x, which is a function of x, and it's times by e to the minus 3x. That's a function of x. So we need to use the product formula which we used in a previous presentation. The product formula states that to find the dy by dx, the differential of y with respect to x, we have a formula of u times dv dx plus v times du dx. We have to define a u term in this expression, and we have to define a v term. My u term I'm going to let be 2x, and my v term I'm going to let e to the minus 3x. If you're not sure about this process, I would encourage you to visit the previous presentation on the product rule. When we differentiate u with respect to x, we get 2. That's standard forms in our table. I've just put the table down here for convenience, a standard polynomial there. And when we differentiate e to the minus 3x with respect to x, again dv by dx here, again from the standard table, here the e to the ax, we get a e to the ax, we get minus 3 e to the minus 3x. Okay, just following that standard form through. Then to find the differential dy by dx, we have to, from the formula, multiply the u, which is 2x in this case, by the differential of v with respect to x. That's the minus 3 to the minus 3x. And then we have to add to that the v term, which we said was e to the minus 3x, times by the differential of the u with respect to x, which is 2. Just tidying it up a little bit, dy by dx is equal to minus 6x e to the minus 3x, the 2 times the minus 3 gives me minus 6 there, and then I just brought a 2 to the front of the second term, plus 2e to the minus 3x. Exercise 4, part C. We're now going to find the second differential. I've just rewritten the first differential from the previous slide for convenience. So dy by dx is equal to minus 6x e to the minus 3x plus 2e to the minus 3x. Note the first term here on the right hand side, the minus 6x e to the minus 3x, is a product again because we have a function of x times a function of x, the minus 6x times the e to the minus 3x. So that's the product. The second term is not product because it's a constant 2 times by one function of x e to the minus 3x. So for the first term, we're going to have to use the product rule again. So I need to define a u term. So I'll let u equals to minus 6x. So when I differentiate u with respect to x, I get minus 6. Standard forms again, standard derivative tables we're using. I'm going to let v is equal to the e to the minus 3x. So when I get v by dx, I get minus 3e to the minus 3x again, following the standard forms for it. So my second differential equation, my d2y by dx squared, looking at the product rule, I get the u, the minus 6x, times the dv dx, the minus 3e to the minus 3x, plus the v, the e to the minus 3x, times by the differential of u with respect to x, which is minus 6. Don't forget, I've also got to differentiate the standard form 2e to the minus 3x, so that's how I get my minus 3 times 2e to the minus 3x. Again, I'm following the standard form through for the exponential function. I'm just tidying up here. I get, on this line here, I get equals to the 18, which is the minus 6 times the minus 3, x e to the minus 3x. I'm just bringing the minus 6 to the front of this term. I get minus 6 e to the minus 3x, and then tidying up the last term, minus 3 times 2, minus 6 e to the minus 3x. Tidying up still further, bringing my like terms together. The last two terms are like terms, so I get 18 to x e to the minus 3x, take away, and I got minus 6 e to the minus 3x, take away minus 6 e to the minus 3x, so that gives me minus 12 e to the minus 3x. So I found my second order differential equation now. Exercise 4, part D. The y double dash, the second differential from the previous page, is repeated here for convenience. It's 16 times sec cubed of 2 theta plus 16 times sec 2 theta times tan squared 2 theta. We're asked to find the value of the second differential, the y double dash, when theta equals to 0. All that means is we need to put the value of theta equals to 0 wherever we see a theta in the above line. And there are 3 positions where that occurs. I'll leave you to do the number crunching on this, but basically what you will find is the sec cubed of 0 will go to 1, and the tan squared of 0 will go to 0. So the second term will disappear because you're multiplying the whole thing by 0, and the first term will become 16 times 1, giving us the answer of 16. Here are some further successive differentiation questions for you to have a look at. I would encourage you to do as many as you possibly can. The answers are in the square brackets. Thank you for viewing.